I also should emphasize that I'm technically not a mathematical physicist, so I'm really happy to be here to learn all these concepts, and I'm happy that Paulo established actually all the convergence results or assumptions I need. So what I will do in my talk, I will focus on the concepts rather than the exact mathematical proofs, but I will try to point out the subtleties that will arise when I go through it. And what I'm basically going to show you is, I'm going to show you a strategy that is only possible in infinite dimensional systems. So you need unbounded operators. I'm first going to argue basically in finite dimensions not possible. Then I go to infinite dimensions and I develop that scheme. And then in the end, I come back because I will discuss one potential application of that. And again, the goal of that scheme is to speed up quantum dynamics. And before I define what that is, let me actually start with a question. I want to start with the question, can we actually do the opposite than dynamically coupling? So how did Paulo introduce that? Paulo basically introduced it as a mechanism to average out interactions, or more generally, to average out Hamiltonians. Since I'm a physicist, let me motivate that a bit more from a physical perspective. So what you see here is actually two platforms for quantum technologies. One is trapped ions, and it's an old picture by Rainer Platt and David Wineland. Whereas the other one is NV centers, which is a very promising platform for sensing. Also an old picture by Jörg Wachtrup. And so what is the problem in your system? So particularly see that here nicely, that here you have electron spins sitting or are surrounded by nuclear spins. And these nuclear spins actually introduce decoherence due to the interactions of the electron spins with the nuclear spins. So what does then dynamically coupling try to achieve? Well, we apply some pulses, say, on the electron spins here and here, and we try to do that fast, such that these interactions around it are averaged out. By that, you can actually prolong coherence times, and has been successfully demonstrated, particularly in nuclear magnetic resonance. But the key point is that you apply some controls, here some shape fields, and you do that fast, such that these interactions are averaged to zero. And Paulo nicely introduced that, but basically what we want is we want a mathematical technique such that we have an interaction described by some Hamiltonian H0, and that control strategy implements some map that averages this Hamiltonian to zero. So in this setting he introduced here before, I assume that H0 is traceless. And we know, well, if we do that fast, we can describe the map by this average, and described by fast unitary kicks. Remember, that comes from the Trotter limit, this average. So what I basically assume throughout the talk is that this limit exists and that it converges. I will comment on, again, the subtleties when I go to infinite dimensional systems with this problem. All right, so, well, you can show, and that started by work by Viola et al. In the 90s, that such a couplings that always exists. Basically, two design, one design, as it was pointed out before. And we could basically just take an irreducible representation of the unitary group. You map onto the commutant, and the commutant is true. In this case, you map everything to the identity. That's right. You can always construct such a set V where you take your unitary transformations from. Well, the first question you may ask is, what if you have an infinite dimensional system? What if your Hamiltonian H0 is infinite dimensional? Well, as Robinson pointed out already in Paulo's talk, for infinite dimensions, such a decoupling set, which is actually assumed to be finite, finitely many elements, does not necessarily exist. So what that means is if you have, say, a quantum harmonic oscillator, you cannot stop the oscillator rotating or oscillating. That is the physical intuition. The reason for that is because the spectrum is basically positive and unbound. All right, so but I was wondering if, when you look at that, I was asking, well, can we actually do the opposite? And what do I actually mean by that? By that I mean is, does there exist a control strategy, a set V of unitary transformation in the simplest case, that achieves the opposite of one? So how do I define that? Well, let's say we construct a map that maps H0 to something like lambda strictly larger than 1 times H0. And we called that strategy, we introduced it in 2020 in this paper, Hamiltonian amplification. I must say, I think Daniel came up with this idea, and going through around the world selling the Hamiltonian amplifier, many people don't like that word because especially David Wineland, the Nobel laureate, pointed out that actually you need a medium to amplify. So if you're not happy with that name or that word, just see it as the opposite of dynamical decoupling. So potentially a better word would be dynamical amplification. So the first question you may then ask, is that actually possible? Can we construct? Yeah.
To interrupt, is the M allowed to depend on H0, or should this be even universal?
No, okay, that's a very important point. Thank you. So the key point of dynamic decoupling is that it actually holds for all H0, which is important because you often don't know what the structure of this interaction looks like, right? So that's why it's important to have a strategy that does not explicitly depend on the type of Hamiltonian or the interaction. And in a similar fashion, I assume that here. Because otherwise it's actually trivial, which I will comment on it later, right? Because otherwise you construct another Hamiltonian and you add it, you have 2 times H0, done, we have amplified it. Well, surprise, surprise, right? But of course that depends on the knowledge of H0. So I assume I don't know H0. All right. And again, the first question is, does it actually work in finite dimensions? Any guesses? Especially for the TP map people. No, right? Because when you look at that map, that is a contraction. So if you take the norm on both sides, well, so this is the goal. If you take the norm on both sides, you see that it is upper bounded by the norm of H0. So in other words, this can never be true in finite dimensions. Again, it holds for any unitary invariant norm. So we could basically stop and say, thank you, that's it. I showed that it is impossible to speed up a quantum system. By that I mean amplifying that Hamiltonian, if I don't know. But of course, that rests on some assumptions. So first of all, if you look at that picture now, if you apply some controls here and you want to amplify that coupling to something like lambda times g, that idea must explode in your head because of that. So you have to go back to your desk and think. What is the assumption? Of course, the assumption is, well, that everything is bounded. So the question is, what happens if you have unbounded Hamiltonians for which this doesn't really make sense anymore? And that is particularly important because in the strapped ion setting here, the interaction between these ions, which you see here is the fluorescent light of these ions they're emitting. The interaction between the ions is mediated through quantum harmonic oscillators, namely through the harmonic motion. And the quantum harmonic oscillator is described by a Hamiltonian that is unbound. So naturally you wonder, well, what about unbounded Hamiltonians? And I'm going to show you that in fact for that it works. All right, but first, here you go.
This is only a test.
Should have emphasized it before. Sorry. Well, I missed some sort of definition here, I guess, then.
To test the fire alarm, it's to test the speaker.
How many actual fires happened during
So mathematicians just freaking out that I'm not defining things well, I guess. All right, all good? Okay, so the question is, again, in infinite dimensions for unbounded operators, can we actually construct a scheme that achieves that? Right. But first you may wonder, well, I'm making assumptions here, namely the assumption that I have this delta function like kicks, which polar called bang bang or unitary kicks. And generally you may wonder if there is a general control strategy that achieves that in finite dimensions. And at first, I'm going to show that this is indeed impossible if you even generalize that. So I first gonna formulate that question in a control theoretic setting, and by that I mean in a time continuous framework. Based on that, I show that it is not possible in finite dimensions, which is a one-line proof, actually. And then I go into infinite dimensions, and I show that indeed there it is possible, and I explicitly construct the scheme that achieves it. I will write down some Hamiltonians for which I can do that, and it is an open question how large that class actually is, and I would ask you that, and I propose that as an open question. I will derive bounds, which is in this case, in this setting, relatively easier, so I don't need to do any of this, which I will argue later. And then I go on and I show actually an experimental demonstration of that, because recently the ion storage team at NIST have demonstrated that it actually works. And what they actually showed is that you can speed up Rabi oscillations with that procedure. In the end, I'm gonna come to another application which I think would be interesting, namely speeding up photonic quantum computing. And I just briefly go over it as a potential application. But in the end, I want to conclude, and I particularly want to open up the discussion with a question about the relevance of infinite dimensional system in applications. Because I got the question a lot that, well, does it depend that we have an infinite dimensional system or not? So it shouldn't depend on red, right? Because from an experimental point of view, we have finite energy, we have finite dimensional systems, finite beam many levels. And I want to open that discussion posing some questions. All right, let me start with the control theoretic setting, and actually following this approach by Todd Brunn and Daniel Leder in this book, called quantum error correction, particularly the chapter about dynamically coupling from Lorenzo Riola. So for those of you interested in dynamically coupling, that is also a good reference. It's not super rigorous in a mathematical sense, but at least to get the idea from a physics perspective, take a look. So what is the setting we have here? Well, we start with some time-dependent Hamiltonian HT. So and I assume, let's say H naught is a Hamiltonian, I don't know. Well, it could be some interaction, it could be something describing the system, which in the end I want to amplify or which I want to decoupling. But I also add some time-dependent Hamiltonian, which I call a control Hamiltonian, which could, for example, describe some time-dependent fields, magnetic, electric, whatever, that couple in some way, for example, to the dipole, to the system. And so I want to come back to that question now about the coupling and amplification. So first of all, if you want to formulate amplification, you somehow need to rule out the situation that we can just say HC of t is H naught, right? Because then again, we have the situation, we have 2 times H naught, oh, we have amplified, right? But of course, that requires knowledge about H naught. I need to design the controller in this setting based on H naught. And I want to rule that out. And how do I rule that out? I rule that out by going into a frame by rotating with HC of t. So I define a unitary transformation generated by this HC of t, with which I rotate. And in that frame, the evolution is given by this expression. So my time evolution is just the time order product. By a new Hamiltonian that is rotated, UC is generated by HC of t. And then we take the integral from 0 to t. Right? Again, that is, I just do that to rule out the situation that I can actually just add some multiple of H naught here. All right. Well, to avoid that time order product, there's a convenient way of doing that, and that is through the Magnus expansion H bar of t. Again, assuming that the Magnus expansion converges, and you can write down criteria for that. All right. Okay, so now that allows me, first of all, to define dynamically coupling in a time continuous way. Well, it means dynamically coupling means that this H bar of t is either equal to the identity or multiples of the identity, such that we just have a global phase or so. Whereas this amplification would be this, right? We want to have H bar of t, which is this average before lambda times H naught. Lambda slightly larger than 1. And first I want to show you, and that is a one-line proof, that is actually impossible. And the idea of this proof is already in this paper by Dan and Lida. And the observation is that you can always write down a set of unitary transformations, a family of unitary transformations, such that you can write H bar of t as this. So what this achieves is you get around the time ordering. So you probably know that the Magnus expansion contains all these higher order nested commutators. But you know that there exists this W of S such that you can get rid of that. What this W of S is, of course, that is not clear. But the fact that it exists means we can, well, basically take again the norm on both sides, use the triangle equality, and we again have this. So what that implies is that there does not exist a controller that achieves Hamiltonian amplification in a finite dimension setting.
Excuse me, can you say something about the UC versus the U?
Oh, so yeah. So the UC,
If it's an SDE, then I understand what it's the same C on both sides, but
so the UC is just the unitary transformation
what?
generated by the HC of the
HC,
Yeah,
okay.
yeah. So it is basically evolution generated by the
No, that's
controller.
fine then. Sometimes they try to solve it with the same C on both sides.
Oh, okay, no. Oh, with the same. Say again.
The left C is the right C.
The left C is the right C.
Use anyway, you could,
Yeah, so it's generated by HC.
no,
Right. It describes the evolution of the controller alone. All right, so, and the trick is really to show that this is impossible in finite dimensions in this general setting if you know that there exists this family. And the proof is fairly simple, actually. In this paper, they discretize, take the limit, and you can always construct that. Taking the norm of both sides implies that this has to hold, which in turn implies that this cannot hold. In finite dimensions, right? Because in infinite dimensions described by monoid operators, that norm explodes. All right, so let's take a look at that. And first, I'm going to build up the theory step by step. I start with the simplest case. In quantum optics, we would call it displacements, which is basically a linear combination of the position and momentum operator. Then I look at the simple interactions, and then I go to quadratic Hamiltonians, right? And let me introduce the setting. So the setting is basically the setting of dynamically coupling. We apply unitary kicks V from a set VA VHA, which I call now the amplification set, as an analogy to the decoupling set. And again, crucial assumption here, I assume that that limit exists, but technically speaking, in infinite dimensional case, we have to worry about the domains. I assume that holds. Okay? All right, so then we know that the evolution is actually governed by this map, which I call the amplification map. And it's the same as before, just that we want to amplify rather than decouple. All right. So this is a crucial object which I will continuously refer back to. So again, I'm always talking about this set and how we can choose these fees. And the crucial transformation I'm utilizing is the so-called squeezing transformation. So what does squeezing do? Basically, squeezing stretches and shrinks the position and momentum operator to quantum. It is defined, or I call it S. It's a unitary transformation. And I use these superscripts plus and minus to show that, say, if you have the position operator X, it either gets kind of attenuated or amplified by a factor e to the plus minus plus R. R is a real number here, which you call a squeezing parameter. Okay. Notice though that if you say we amplify X, attenuate P. For those of you who are not familiar with this transformation, that is the key in quantum optics for precision measurements, for amplifiers in general. So parametric amplification is nothing else as this. You can even think of it classically. Take a pendulum along and change the length of the pendulum. Only the oscillator is sped up. That's pretty much what's happening. So you see already, without actually even going into the Trotter framework here, you see already there exists a transformation that achieves this amplification. All right? But then you could ask, okay, let's make it a bit more complicated. What about linear combinations between the position and momentum? You can ask, does there exist a unitary transformation that amplifies in this setting X and P at the same time? And the easy answer is no, it can't exist. Because otherwise you would not preserve the canonical commutation relations. And that is exactly the reason in the quantum optics language why a phase-independent amplifier for one mode cannot exist. But let's take a look. What about if we alternate between squeezing along X, say the plus and minus? Well, then we get here something like e to the minus R, e to the plus R, but then we can do the opposite, can create that sum, and then we get something like cosh. So if we alternate between squeezing along X and P, which I call plus and minus. So say you first apply plus, you get your S plus, you sandwich that, e to the minus R, e to the plus R, and then you do it by minus, in the end you get cosh. So that shows that this set composed of these two transformations achieves the amplification of these linear combinations. That's already something interesting, even though rather trivial. It means that you actually can do phase insensitive amplification. So in the quantum optics language, you define a displacement operator like that. Alpha is just a real number. A is the Bolognese operator, which is just the X plus IP. And independently of what that alpha is, or the phase of that alpha, if you just do that, you amplify this displacement. All right. But note that I amplify A and A dagger at the same time. That means I could just replace this complex number by another operator coupling B. So I could at the same time also amplify these interactions by doing that scheme. Because I don't need to know what the B is. I just replace basically the alpha star with an operator, or the alpha. All right. So the key point here is that in this case, you don't even need to Trotterize, because if you look at the commutator between these rotated evolutions, that just gives you just a phase. In this case, though, since we have an operator here, we need to Trotterize, and that's where the usual domain assumptions come in. So when I say it is independent about the knowledge of B, well, of course, I need to assume that Trotter converges, and therefore I need to define some domains over which this is valid. So explicitly, I need to have some knowledge about B, right? Just to verify. And so the question is, how far can we push that? Let's consider the quadratic Hamiltonian of that form. So what you have here is xi and xj, again, are position operators acting on each of the modes, which I will call different harmonic oscillators. P is the same. So basically, it's just a bunch of interacting harmonic oscillators. Notice that if I apply now squeezing on I and j, well, you get e to the minus r here, e to the plus r here, and then I can do the same trick. So that immediately shows that if I alternate between squeezing and x and p, but on all the oscillators, I amplify the oscillator system by cosh 2r. So overall, what that means, I speed up potential evolution generated by this Hamiltonian because I don't need to know these real constants alpha and beta. All right, so you might have noticed for those people who are familiar with quadratic Hamiltonians, this is not the most general form of quadratic Hamiltonian. The most general form is actually given by this, right? You have a sum in J with some symmetric matrix, which is real. And then you collect the position and momentum operators in just a vector, which I call. All right, again, A is my symmetric matrix, which basically contains these couplings alpha and beta. So what you notice here is if you look at this form, what is missing here is actually the cross terms of X and P. And with these operations, you cannot amplify these cross terms because you see if you have something like xi pj, if you now amplify xi and pj, you get a plus and you get a minus, which cancels. So these terms are left invariant. However, if you change the direction along which you squeeze, if you define an angle, then you can amplify them. However, what is an open question, and I'm not even sure if that exists, a set like that. I haven't found a set yet that allows you to amplify a quadratic Hamiltonian, an arbitrary quadratic Hamiltonian. Not even sure if it exists. It depends on really days. When I get up in the morning, sometimes I think, oh yeah, it must work. But sometimes I feel like, there must be something which can't work. So an open question is, in general, for which Hamiltonians, starting with the quadratic ones, can we construct a finite set of unitary transformations for which we can amplify that Hamiltonian? If you have any ideas how to address that question, please let me know. Again, the first question is start with the most general quadratic Hamiltonian rather than a special case. All right. Again, I would stop here and introducing schema. I want to come to a next question, which is about convergence, actually. And that is about error bounds. And we heard already before that it's actually challenging in an infinite dimensional setting to derive error bounds. Here, though, for quadratic Hamiltonian, it's easy because you can use just a symplectic representation. I just take my matrix A, which is symmetric, collect all the constants that I have in this matrix. Then I have a transformation not over the unitary group anymore, but over the symplectic group. And for that, I can apply the usual Trotter bounds. So what I could do is I could just define an error, which is just given by the Hilbert-Schmidt distance, which shows the amplified evolution by cosh 2r, omega is the symplectic form. And this is basically described as scream in the symplectic setting. And just going back to the old works by Suzuki, apply these, which is general on a Banach space, right? And then you get a bound of that form. So first of all, notice that omega max here is basically the largest constant in A. It depends explicitly on how much you amplify, namely on the sinh R. It depends also on how many oscillators you have, namely N. And it depends on delta T, which is this 1 over M dependence. M is the number of kicks you do. All right. But notice that you get this exponential factor, which you don't get if you work in a finite dimensional setting on the unitary group. Because then you can use unitary invariance, you get rid of that factor. But here you can't do that due to the non-compactness of the symplectic group. In fact, if you take the squeezing transformations out, the two-mode squeezing and the single-mode squeezing, then you are left basically with your orthogonal group. And then you can have another bound again of that form, but then you can't amplify. You need the non-compactness to amplify this Hamiltonian. In fact, mathematically, that is the reason why the thing works. Right? So if you work just on the orthogonal group, taking squeezing out, then it won't work. However, I believe this is kind of the worst case scenario. So let's first have a look how well these bounds are. Well, here I basically chose a simple harmonic oscillator system with an amplification factor of 2. What you see here is the bound. The red curve is the bang-bang setting with this. But also I developed smooth pulses that show even faster convergence. In fact, that actually resembles a higher order Trotter scheme. I just wanted to say it does not rest on the assumption that I do this bang-bang setting. but I have a smooth pulse of high frequency that achieves the same, and it does it even faster. And I added some noise to show some of this. But what I actually expect is that if you make it state dependent, you get way tighter bounds. So I think, again, as I said before, I feel like this exponential factor is just an artifact of the symplectic group, whereas if you develop Tora bounds that depend on the initial state, you should get a much tighter version of that. And for that, I refer to Alexander, where is he? I think everyone refers to today. So feel free to explain that better, because I think that works really nice here. I think it is still a finite dimensional setting, but it should be relatively straightforward to generalize. Are there any questions up to this point? Because so far, again, I want to emphasize, I want to focus on the concepts rather than the exact derivations. If there are no questions, then I want to ask another question. Well, I motivate this thing by, instead of decoupling, suppressing interactions, we want to amplify these interactions. But what is the point of that if we also amplify at the same time the interactions with the environment? So if we speed up decoherence in the same way we speed up the system dynamics, we didn't get anything. All right, so let's take a look at that. So what I'm going to do now is I'm look at basically an open system composed of a system S that interacts with an environment E. And what I assume is that this interaction with the environment is also described by some quadratic Hamiltonian, which is standard assumption actually quantum. Right. So again, I assume that my interaction with the environment takes this form. I is now the system, E is the environment, such that my total Hamiltonian takes this form. And if I then do amplification, well, I see that my system gets a factor cosh 2R versus my environment gets a factor of R, of cosh R. So it's amplified in a different fashion. Well, if you look at that, basically think of two harmonic oscillators. Well, I wrote down the classical picture here, but so in the middle, we amplify this interaction by cosh 2R, this by cosh R. What it means though is that if you look at times like that, we exponentially suppress the system environment interaction. Well, but you may not ask, okay, what if I want to do that for, would I want to have that for arbitrary times? Right? What if I want to have amplification, but at the same time, for all times, suppressing the system path interaction? And naturally, we can ask, well, can we, for example, combine dynamic decoupling with Hamiltonian amplification? And let's take a look at it. And first of all, what did I say in the beginning? I said in the beginning, for infinite dimensional systems, dynamically coupling does not always work. That is true, but there are interactions, namely the quadratic ones, which you can decouple. And the scheme is very simple. So the scheme was actually developed even in the 90s by David Vitali and Paulo Tombesi. And what they actually done is they just said, well, let's rotate the oscillators fast. And the rotation is just described by this product of local rotations of the oscillators. All right. Again, this is just a degree, the normal harmonic oscillator, and phi is how much we rotate. The decoupling set that achieves decoupling is just the identity, and then a rotation around pi. Why? Because that inverts the sign in front of x and p, and then we alternate between that quickly. You do that, the decoupling map, again, but Paulo introduced at the beginning, takes that form, it averages out the system environment interactions. And then you can easily see where we can combine that. We just can compose these two maps, and then we get basically an amplification of the system, and the system environment interaction is suppressed at the same time. All right, so in the end, we have four operations. They look like that, versus the scheme looks like that. In the bang-bang setting, we apply squeezing here, and here we also additionally rotate, which achieves amplification of the system while the interactions are suppressed. All right, that is nice, but from an experimental perspective, does it actually work? Can we actually do that? And the next thing, and I want to quickly go over that because it has been actually experimentally demonstrated in 23. Literally, I think that paper came out a month ago or something. Although the experiment was done 3 years ago, it took some time to get the data. Yeah.
So in your previous slide, the decoupling acted on the bath, or because it's simultaneously with the two?
No, here I only act on the system.
But the amplification and the decoupling happen simultaneously, right? Like from the figures, or am I wrong?
What do you mean by so
So at the same time, you do the amplification procedure and the decoupling procedure. I mean, it just looks like it. I don't know.
I mean, so what you just have a bunch of pulses here, right?
Yes.
So one pulse is this parametric pulse, the squeezing, and the other pulse is the rotation.
I see. So you do it one after another
Yeah.
one.
Just to visualize. You could also do it at the same time, basically in this time continuous setting, but this is the simplest version. Any further questions? Then I would just go on and just quickly show you the experimental demonstration of that. And what they showed is, besides this phase insensitive amplification, they also showed, and that is, I think, the more impressive result, the speed up of Rabi oscillations. So what are Rabi oscillations? What they looked at basically is they looked at amplifying the Jaynes-Cummings interaction. What is that? Well, we get a quantum harmonic oscillator that interacts with a two-level system described through that Hamiltonian. And that induces oscillations between the system due to the energy exchange. That is called Rabi oscillations. The setting was an ion trap, so nowadays they look like that. That's why I showed that old picture in the beginning. Today they're on a chip. And what you do is you put the ions in there, you load them in here. The harmonic oscillator is the radial motion of the trap, of the ions in that trap. And how you do the squeezing is basically you took the trap frequency and you do this. You do that fast. That's why. And you do it twice the frequency of the harmonic motion. All right. The qubit or the two-level system is basically some hyperfine manifold, some states there. And the interaction is the coupling between the motion and the two-level system.
Can I ask a question? So I guess the Jaynes-Cummings model comes from, let's say, the quantum Rabi model through some rotating wave approximation.
Yeah.
And then if you start amplifying it, you get to the regime where the Jaynes-Cummings is no longer a good approximation?
Yeah.
Or, and you
Well,
see this in the experiment? Or
No, I mean, let me show you the plot. So first of all, we used m equal to 6 Trotter steps, which is not much. And those are, so the blue curve is for no squeezing, right? The normal Rabi oscillations, and the speed up is marginal, right? So in fact, it's just a factor of 3/2. So that's really a proof of principle one. But of course, at some point, if you amplify more and more, you get into the strong coupling regime, right? Where you at some point cannot throw away any more the counter-rotating terms. What happens then, and when you see that, I have no idea.
so I guess my question is, if you fit this not with Jaynes-Cummings, but with quantum Rabi, would the fit be better for this plot?
I doubt it because of this small factor. But yeah, good question. I don't know. I think you need to amplify much more. It was like G over the different frequency, right? And by 3/2. I don't know. All right. Any further questions? Again, I find that still, when I first reached out to them, I want to make two comments actually. The first comment is the importance of treating infinite dimensional systems properly. Because the first question David Winan, the Nobel laureate, asked me, how fast do you have to do that? How fast do you have to apply the squeezing transformations? And I basically said what everyone in textbook dynamical decoupling says, faster than the fastest coupling or the fastest constant in the system. But then wait, I did my PhD with Daniel, unbounded operators. No, so actually it depends on the initial state. So in the end, I couldn't give him a rigorous answer because it depends on the initial state, since we have an unbounded Hamiltonian here, which again emphasized the importance of developing Trotter bounds in an infinite dimensional setting to know how fast you need to be. And then I gave him a hand wavy answer and said, look, the higher order terms scale like that. So 1/n, so should be good. And it works. But if you amplify more, I have no idea. So what is a question left is developing this Trotter bounds, specifically for the Jaynes-Cummings model, for example. All right, so let's step back again and let's move on to something I think more interesting, because proof of principle. So can you actually use that to implement quantum algorithms faster? And first of all, so far, when we talk about quadratic Hamiltonians, it's very well known in the community that this is not enough for universal quantum computing. So these quadratic Hamiltonians generate Gaussian operations, and they are not universal. What you need is a nonlinear term. And by nonlinear, I mean higher order than squaring. So you need something cubic or something. In fact, I think Seth Loy showed, it's not really rigorous, but I mean, sorry, well, it's a nice paper, but it's
Yeah, you can say it.
Oh, it's basically calculating commutators and using Trotter without talking about domains and stuff. So assuming convergence and all that kind of stuff. But basically, take one nonlinear term and you get universality. But before that, it was very well known. It actually goes back by Nielsen and or by Isaac Chuang and Yamamoto. Is that you take the so-called cross-current action, you get universality. So that paper is actually really beautiful. It is called a simple quantum computer. Use beam splitters and phase shifters, basic quantum optical elements, and you add that nonlinear term, which is an interaction between one mode with one harmonic oscillator described by A dagger A, and the other oscillator described by B dagger B. If you add that term, you get universality. The problem, though, is that these interactions require way high, I think, fourth order interactions. So high to the 4 or something materials, which means they're really, really weak. So that's why the paradigm shifted a bit to non-deterministic schemes. But originally, I think that proposal is really beautiful because it's very simple. The problem to implement that is that chi is usually very small. So what you could use is actually just the scheme I proposed, because you can amplify this A dagger A, right? And well, how do we do this? So first of all, what would be the naive way? The naive way would be you just take this cross-curve Hamiltonian that generates a unitary transformation. You just repeat that. If you repeat that, say up to e to the I pi, then you can show that this creates a controlled phase gate in the computational subspace spanned by zone 1 to 2 the Fock states. But if you just take one of these and insert squeezing and do that m times, you can actually approximate that and you can significantly speed up the rotation of that. How do you find the error? Well, you take the ZZ gate in this 4x4 subspace, you project onto that with these projectors, and then you calculate the Trotter error. That's what you find numerically. It's good. So in the end, I'm currently working with a collaborator in Tucson in Arizona to implement that scheme based on optical fibers, actually. A little bit challenging to do that, but I don't think it's impossible. But what that actually means is what have we shown? Let me make a bold claim. Well, I showed that you can amplify these guys, right? Well, not all of them, but basically the ones that allow you to do the phase shifters and the beam splitters. So I can amplify these gates. I can amplify this. So in the end, I can amplify the generators of a universal gate set. What that actually means is if I assume that I can do squeezing in no time, and arbitrary fast and arbitrary strong, you can do basically arbitrary quantum computations in no time. Of course, there are caveats to that. I make the assumption is that I first of all associate a time to this generator, right? But if I get squeezing for free as a resource, then I can take my whole quantum algorithm, insert these squeezing transformations, and shrink it and make it shorter and shorter. And in the end, the speed of that algorithm, or the depth, shrinks more and more. And I could actually put that depth to 0 if you want. Again, that is under the assumption that I can do the squeezing arbitrarily fast, arbitrarily strong. But I think it is an interesting point that it emphasizes how important actually squeezing is. And when you look at the original works by Seth Lloyd, he actually says in the end, what would be the advantage of a photonic quantum computer? Well, we could potentially speed up these computations. That is pretty much the last sentence of the paper. And indeed, doing that scheme could be possible. And since I have 5 minutes left, let me sum up. So what I showed, well, what I argued basically, I didn't prove anything. I argued that you can speed up infinite dimensional systems, whereas finite dimensional systems is not possible because of these non-bounds, right? And I positioned that scheme as the opposite of dynamical decoupling. So a potentially better word would be dynamical amplification. But let's call it Hamiltonian amplification and stay with that word. What does it achieve? Well, you enhance couplings without actually knowing what these couplings are, without really knowing what these interactions are. You can do phase-independent amplification. And you can speed up Rabi oscillations. At the same time, you can combine it with dynamic decoupling. Although, to the best of my knowledge, for the continuous variables, nobody has implemented in a lab dynamic decoupling. There are some challenges associated with that, and I can talk about that later. But in the end, if you could do that, you could actually do quantum computations faster. You can speed them up. And with that, since we have a few minutes left, let me start with some open questions. So well, should I start with the philosophical one? Well, when I gave a similar talk at NIST before the experiment. right? And I basically said, look, in finite dimensions, you can't do that, but in infinite dimensions. And then the experimentalists all say, wait. That can't be right. How can it depend on our description of nature that we can do something versus in the other setting we can't? Because the argument was, well, in the lab, we have finite energy. We cannot excite infinitely many levels. So in the end, a finite approximation of that should be fine. So how can we actually describe that limit? How can we go from finite dimensional systems to infinite dimensional systems? Because it shouldn't be an up to up transition, it should go smooth, right? And I think an interesting way of studying that is going from, say, angular momentum operators to bosonic operators, to the Holstein-Pierre-Markov transformation. And I was always bothered by that, because when you read like Arenz matter books, or I don't know a single reference that does this transformation going from a finite dimensional system to an infinite dimensional system rigorously. So what you actually want is, first of all, you want an error bound on that. But on top of that, it would be nice to have at the same time a Trotter bound for it. So on one hand, you want to have a Trotter bound that depends on the number of spins that form these angular momentum operators, such that in the limit n to s to infinity, you get this exact bosonic operator. But at the same time, you want to include that Trotterization. So I think that is a challenging question. And I don't know a single reference or not even an idea how to do that. So that's why I think I'm glad to be here, because for that you need sophisticated mathematical techniques, which I'm still learning. All right, with this, I want to thank my group, particularly Ankit, who does all the numerical simulations and digs deep into unbounded operators. And he's the one I talked with a few of you about it. And he asked me if I should take a functional analysis class. And I basically said, let's do it together. I'm really glad that I have him. I also want to thank Daniel, who was really helpful in developing the proposal, and Cecilia, who knows a lot about quantum optics. And my advisor at Princeton at that time, Herschel Rabitz and Dennis Bonner, who are great quantum optics people or quantum control people. At the ion storage team at NIST, who finally carried out the experiment. Well, this I also want to thank you, and I hope I was not too vague, and I hope I could communicate what I want. Thank you.